Hi, Mr. Green here. I'm going to take you through this next screencast, which is in the forces topic of the Physics AQA GCSE, and this refers to pressure in fluids. Our learning objective is to know how to calculate the pressure in a fluid, so pause the video whilst you write that as your title. Okay, got some retrieval questions to start with, so if you pause the video and attempt those 5, you can then carry on and unpause the video when you'd like the answers. Off you go. Okay, question 1. The equation for elastic potential energy. That's elastic potential equals half times spring constant times extension squared. Question 2. What is meant by a moment? Moment is the turning effect of a force. What's meant by a pivot? A pivot is the fixed point around which the force turns in a moment. Question 4. What's the equation to calculate a moment? Moment equals force applied times the perpendicular distance from the pivot. And finally, how can we balance a clockwise moment? We apply an equal anti-clockwise moment. Okay, so today's learning outcomes are to be able to calculate the pressure in a liquid, to be able to describe what happens to the pressure in a liquid as you go deeper, and to be able to explain why the pressure in a liquid is greater at the bottom of a liquid than at the top. Okay, so calculating pressure. Liquids and gases are referred to collectively as fluids. And the pressure in fluids causes a force that's normal to the surface. That means it acts at right angles to it, at 90 degrees to the surface. To calculate the pressure at the surface of a fluid, we use this equation. Pressure equals the force normal to a surface divided by the area of that surface. Pressure is in pascals or newtons per metre squared. Force normal to the surface is in newtons, and the area would be in metres squared. Okay, so with that in mind, could you pause the video and attempt the following calculations? Questions 2 and 3, you'd have to rearrange the equation. Off you go. Okay, question 1. Answer for A is 0.83 pascals. B, 200 pascals. C, 46 pascals. And D, 0.1 pascals. Question 2. The force in the following examples. For A, it would be 4,000 newtons, and for B, 3 million newtons. Question 3a. What's the area in these examples? So for A, it would be 0.33 meters squared, and for B, 240 meters squared. How does the depth of a fluid affect the pressure? So if you draw that diagram and show the path of each liquid emerging from each hole in the beaker, so you've got the liquid in the beaker there with 3 holes, try and show me the path of the liquid that emerges from each hole. Pause the video whilst you attempt that. Okay, that's how it should look. So at the top it comes out with very, very little force, but the one at the bottom, lots and lots of force. Can we explain why that happens? Pause the video whilst you attempt that. Okay, so the pressure of that fluid increases as the depth of the fluid increases. The pressure of a liquid is due to the weight of the column of liquid above it, and as we increase the depth, the weight of the liquid above increases, and that increases the pressure. Okay, so with that in mind, could you answer this question? Giving you a diagram of the dam there, why are the walls of dams thicker at the bottom than at the top? Pause the video whilst you attempt that question. Okay, particles in a liquid are really tightly packed, so the pressure acts in all directions. So the pressure acting on a dam at the bottom of the reservoir is much greater than the pressure acting nearer the top. At the bottom you've got the weight of all the particles above it pushing down as well, increasing that pressure. So this is why dam walls are thicker at the bottom, because the pressure is much higher at the bottom of the dam than at the top. Now when we measure the pressure of gases like that of the air in car tyres, we normally make that measurement relative to normal air pressure, so we do a comparison between normal air pressure and current air pressure. Liquids can be measured against normal air pressure, so we can also measure their pressure against that. The pressure difference can then be calculated using this equation. Pressure equals the height times the density times the gravitational field strength. So the height of the column of liquid multiplied by the density of the liquid multiplied by the gravitational field strength. Pressure is in pascals, height is in meters, density in kilograms per meters cubed, and gravitational field strength in newtons per kilogram. Please pause the video whilst you take that equation down. Okay, if we have it in symbols, that's P equals H times rho, that's the Greek letter rho, which represents density, times G, which is gravity. So as a quick example, the Titanic sank in 1911 and it's now 3,000 metres below the surface of the sea. What would the pressure be at that depth? The information I'd need to know in this case is how deep is it, how much is the gravitational field strength on the Earth, and what is the density of water? Density of water is 1027 kilograms per metre cubed. Now I've got that information, I can work this out. So pressure equals height of the column times the density times gravitational field strength. So in this case pressure is 3000, which is the depth, times 1027, which is the density, times 9.8, which is the gravitational field strength. That gives us an answer of 30,193,800 pascals. That is a huge amount of pressure. Could also call that 30,193 pascals, kilopascals, sorry, or 30.2 megapascals. It is a massive amount of pressure that the Titanic is currently under. Okay, with that in mind, you have 4 examples there, questions to do. Could you please pause the video whilst you attempt those questions and restart when you would like the answers. Off you go. Okay, so question 1. A pint of water has got a height of 40 centimetres. What's the pressure at the bottom? Again, we write our equation, substitute our figures. Now remember, 40 centimetres we need to convert to a metre, so that would be 0.4. Density of water is given at the top of the page, times by G, which is 9.8, should give us a pressure of 4,025.84 Pascal. For number 2, again, density of water is the same, but the aquarium is 15 metres deep, so it's 15 times density times gravitational field strength, giving us 150,969 pascals. Question 3. A nuclear submarine can cruise at a depth of 2,000 metres. What's the pressure at that depth? Again, the equation is the same, we're just changing the depth. That's 2,000, so that would be 2,000 times 1,027 times 9.8, which gives us a pressure of 20,129,200 pascals. And finally, a water tower is 400 metres tall. What's the pressure of the water coming out of the pipe at the bottom? Again, we change the height to 400, so that would be 400 times 1,027 times 9.8, giving us 4,025,840 pascals. 3 more questions for us here, and we have to change some of it, so maybe change part of what's happening here. So, pause the video and attempt those 3 questions. Off you go. Okay, question 5. A boat is at the bottom of a part of the ocean. It feels a pressure of 1.2 million pascals. How deep's the boat? So we have to rearrange our equation. Pressure equals height times density times gravitational field strength. So we rearrange that, and height becomes pressure divided by density times gravitational field strength. That's 1.2 million divided by 1,027 times 9.8, giving us 1.2 million divided by 10,064.6. That would be at a depth of 119.2 metres. Question 6. 2 identical ball bearings are placed in a 50 centimetre cylinder, each containing a different liquid. One is placed in sunflower oil with a density of 918. The other is placed in mercury with a density of 13,590. What pressure does each ball feel? So ball 1 would feel a pressure of 4,498.2 pascals. Ball 2 would feel a pressure of 66,591 pascals because the density of mercury is much higher, it would feel a much larger pressure. A ball bearing is placed in a fluid 1.5 meters deep and experiences a pressure of 560 kilograms per meter cubed. What's the density of the liquid? So again, you have to rearrange the equation to make density of the subject. That's pressure divided by height times gravitational field strength. 560 divided by 1.5 times 9.8, which gives us 38 kilograms per meter cubed. So a nuclear submarine can dive to a depth of around 300 meters, and the average depth of the world's oceans is 3,790 meters. What would happen to the submarine if it tried to go deeper than that? The pressure would be far too great for the submarine to withstand. It would start to become crushed and become dangerous for anyone on board. So what's the issue with making a submarine that can dive to 3,000 meters? Pressure at 3,000 meters would be 30 million pascals. The walls of the submarine would have to be extremely thick to withstand that pressure, and if the walls were that thick, it would become really difficult to operate, it would become expensive to build and maintain, and it would have a huge mass, so it would be really difficult for us to use that. Okay, got some exam questions for you to do. Please pause the video and attempt each question. Off you go. Okay, so for this one we have to calculate the pressure on the water at the bottom of the container. Pressure on the water is force divided by area. It tells us force is 27, the area is 0.009 meters squared. Gives us an answer of 3,000 pascals. 27 divided by 0.009. Next one, please pause the video and attempt that. Okay, so the path taken by the water escaping from the centre hole, you needed to draw that. So it needed to come out slightly more than the one above it, but not as much as the one below it. What can be concluded from that about the pressure in a liquid? Well, we can state that pressure increases with depth. Next question, pause the video and attempt that one. Okay, so what we can conclude from this part is that pressure in a liquid acts in all directions, or the pressure causes a force on all the surfaces of that container. Next question, pause the video whilst you attempt those. Okay, question 2a. The diagram will show the height of the water in tubes 2, 3 and 4. What the water would do was reach the same height in each tube as it does in number 1, so the height would look like that, so it would be the same at each point. Further a swimmer dives below the surface of the sea, the greater the pressure. Why? Because increasing the depth increases the height, the mass and the volume of the water column above the swimmer, and increasing the weight of the water acting on the swimmer would increase the pressure. Okay? Next one. Pause the video whilst you attempt that one. Okay, so a person swims from a depth of 0.5 meters to a depth of 1.7 below the surface of the sea. Given the density of the water and the gravitational field strength, calculate the increase in pressure on the swimmer. So we don't want just the pressure, the increase. Correct answer would be 12,112.8 pascals. We get that from the increase in depth. It's gone from 0.5 to 1.7, giving us an increase of 1.2 meters. Our equation is pressure equals height times density times gravitational field strength. That's 1.2 times 1030 times 9.8. Again, you get the extra mark here for adding your unit at the end, so please make sure you put the units on. In this case, it would be pascals or newtons per meter squared. Okay, I hope you found that useful. Please look at any of the other videos on our YouTube channel to revise any of the aspects of physics you need to. Thank you very much for paying attention. See you soon. Goodbye.